Swayam Prabha. Digital India. Educated India.
So students, we have had 8 lectures so far on this topic of consolidation and settlement. Today we come to the last and the 9th lecture on this topic. I plan to wind up this topic with today's lecture by giving you a few more examples of solved problems and highlighting some special instances of consolidation and settlement. I will be going mostly by slides, and let me start with the first slide now. As usual, we will take a brief review of what we have seen in the previous lectures. If you remember, in the last few lectures, we talked about, to begin with, the total settlement and its computation. As you remember, computation of the total settlement is very straightforward, simple, and does not require any elaborate knowledge except the void ratios at the beginning of application of load and at the end of application. Whereas computation of the rate of consolidation or the rate at which the settlement progresses requires a lot more knowledge. It requires the knowledge of either the so called coefficient of consolidation and how it varies with time, and essentially it depends upon determination of certain parameters of compressibility from the odometer test. So, if you remember, we saw details of the odometer test, how to compute the compressibility parameters from them, and then how to compute the rate of consolidation, primary consolidation in particular. Then I also introduced the concept of secondary consolidation and finally radial consolidation. If you remember, the secondary consolidation is nothing but a consolidation which takes place in the form of plastic lag. That is, after the hydrodynamic lag which is arising due to slow flow of water is completed, the plastic flow of the particles and their readjustment starts. Load remaining same, this readjustment goes on for 2 days, 3 days at times, and that is the secondary consolidation part. We also saw an exponential equation with the help of which we can compute the magnitude of this secondary consolidation. And lastly, I introduced 3-dimensional consolidation, the concept. Although concept of 3-dimensional consolidation was introduced, I considered only a very specific instance of 3-dimensional consolidation, and that is the radial consolidation. Let me see. What we discussed was that 3-dimensional consolidation basically involves consolidation in the vertical direction. Suppose this is the surface and you find that due to some load consolidation takes place. In order to facilitate this consolidation, if you install what are known as sand drains, we had discussed this also in the past lecture, then the flow of water takes place due to excess hydrostatic pressure not only in the upward and the downward direction if the downward layer is also pervious, but it also takes place radially. In view of this, there is a tremendous amount of acceleration in the rate at which the consolidation process takes place. Now, how does one estimate the total consolidation that takes place when there are 2 components to it? The vertical component is straightforward, can be computed by the same one-dimensional Terzaghi's consolidation theory which we had seen in very great detail and for which we had seen a few examples as well. The radial consolidation also we discussed, where we calculated UR as a function of time factor TR. Now, if you take a look at this equation, you will find that Vertical consolidation, average consolidation is given by UZ, Z standing for vertical now. If you remember, I had used the same notation UZ earlier to denote the degree of consolidation at depth Z, whereas here this UZ stands for the average consolidation in a layer, but in the vertical direction, that is vertical direction is taken as Z. This is a function of T vertical. T vertical is CV vertical, that is CVZ into small t upon h square. Similarly, analogously, radial consolidation, the degree of consolidation and the time can be expressed by identical equations. In place of h we have 2r. Now, how does one get the total consolidation? Total consolidation is given by this equation, 1 minus u, where u stands for the total consolidation, is a product of 1 minus uz and 1 minus ur. We saw that in order to solve this equation of radial consolidation, we could make either an assumption of free strains in the medium or equal strain in the medium under the applied load due to the preload embankment. We generally use the equal strain technique, which is a much simpler equation to handle, and the solution to this was given by Barron, which I had mentioned in the last class, in the last lecture, and the chart or the table which Barron has given for computing UR as a function of TR is under equal strain conditions is this table. Here, for example, if you know UR, you can, for different values of n, you can find out corresponding TR. Now, what is this n? N is nothing but the ratio of the radius of influence by the radius of the sand drain. Now, the same information was also given in the form of a graph. This graph shows along the x axis TR and along the vertical axis UR. So, if you note any given time t, knowing the compressibility characteristics CVR of the soil and the geometrical characteristics and resulting capital R of the sand drains, you can calculate UR, the radial degree of consolidation. Okay. Now, we also saw, if you remember, one simple example on pre-consolidation pressure. If you remember, I had mentioned that pre-consolidation pressure can be computed from E versus log sigma dash graph. If this A, B, C is the log sigma dash graph, pre-consolidation pressure is determined with the help of drawing a tangent to the straight line portion, then a horizontal and then a bisector, and wherever the bisector intersects this projection of the straight line portion is the point which corresponds to P, the pre-consolidation pressure. That is the maximum pressure to which the soil has been subjected in the past. Okay, now, with this we also saw the example of how to calculate pre-consolidation pressure given the various E, P values. The method is, of course, plot a E log P graph, and following the geometrical construction which we saw in the earlier slide, you can calculate. Now, you may work this out yourself, this example. You will find that you will get a pre-consolidation pressure as 293 kilopascals. Now, with this we will move on to fresh material in today's lecture. What I propose to cover in today's lecture is a few more examples on rate of consolidation, then radial consolidation with and without sand drains, with preload, and then some general interesting information about consolidation and settlement from different instances from the world, and finally a summary. With that, I will be winding up. Let us take a look at the next slide. We will see two examples now on primary consolidation. One is on percent consolidation calculation and another will be rate of consolidation. Let us take example 8. You may need to read it carefully. The dead load on a column due to a chemical plant is 800 kilonewtons, while the live load is 300 kilonewtons. That is the total load. Let us assume that the live load is acting all the time. Let us assume that the construction of the structure is over, the live load has come on the structure, and therefore 800 plus 300 kilonewtons or 1100 kilonewtons is the total load under which settlement is going to take place. The foundation is an ordinary square footing of width 7 meters, that means the area is 49 square meters. The subsurface profile the ground condition below the foundation is shown in a figure which will follow in the next slide. The soil properties which are important from point of view of consolidation are all known. For example, compression index is known as 0.137. Obviously, it is determined for the compressible soil with the help of a odometer test. That is, you will see a soil profile shortly. Samples were extracted from the compressible layer of that soil profile and they were tested in the odometer to get the compression index. The compression index, the initial void ratio of the soil, unit weight and the compressibility parameter CV are all known. Now, what is required is what is the total settlement and what is the time required for 90% of the total settlement. How do we solve this? This is the soil profile. It consists of sandy silt, then a very stiff yellowish brown calcareous sandy silt and then followed by sandy silt containing a small amount of clay. Let us take the layer 3 ranging from 5 meters to 17 meters and to some extent the layer 2 which also contains a little clay to be compressible. That means, we will take the total thickness of compressible layer to be 3 to 17 or 14 meters. We shall solve this problem sequentially. Now, what are the typical steps which are involved? Number 1 is identifying the compressible layer, which I have just now mentioned. 3 meters to 17 meters is the thickness, 14 meters is the thickness of the compressible layer. Then this compressible layer is divided into parts here. So, in this case we shall be dividing this into 2 parts, okay, and let the centers of these 2 parts, subdivisions of the compressible layer, be at A and B. Then next thing is to determine the increase in pressure, that is the incremental pressure that is coming at A and B due to the applied load of 1100 kilonewtons. This incremental pressure we will be calculating using Bushnell's theory and by finding out influence values. Then the total or ultimate settlement we will calculate at point A as well as at point B. The sum of the two will give us the total final settlement in the entire clay layer. And after this, of course, knowing the value of CV, we will determine T90. Okay, how do we determine the influence coefficient? It is very straightforward. We have already seen details of the Bushnell's theory. Here is the foundation. In our case, it is 7 meters by 7 meters. The layers involved are 3 meters and then 5 meters, 7 meters and so on. If you remember, the foundation is kept at 3 meters depth and that means that there is a 2 meter thin layer just below the foundation and water table is at that depth. This is as per the data collected during subsurface investigation. That means below the foundation 2 meters of the soil is dry or may be capillary saturated, but we shall take it as dry, and below that the water is saturated, the soil is saturated. Okay. Now, for point A, if we want to calculate the influence coefficient, as you know, we will calculate A upon H, where A stands for half the width of the foundation and H stands for the depth at which we want the influence value. So, in this case A upon H will be 3.5 by point A is also at a depth of 3.5 meters, and so we have 3.5 by 3.5 equal to 1. Okay. That means the other dimension B upon H will be also 3.5 by 3.5 because this is a square foundation incidentally, and for A upon H equal to 1 and B upon H equal to 1, if you see the Bushnell's chart, you will find that the influence value is 0.175. Now, this is for one rectangle. You know, the loaded area is divided into 4 parts and we are finding out the influence value for this one corner. So, influence value for the total loaded area will be 4 times this, and that is 0.7. Identically, we can find for point B, and that will be 0.16. Next, we know the value of Cc, it is given, and we have divided the layers into 2 A and B, and now the total load of 1100 kilonewtons is distributed over a foundation area of 49 square meters. That means the loading intensity is 22.5 kilonewtons per meter square, and the depth up to point A or point B, as the case may be, or let us say H1 and H2. Now, there is a subtle point which needs a brief explanation here. Actually, when you put the foundation, we will be removing some soil and replacing it with concrete, and then of course backfilling. This is backfill. That means in this portion now, which is being occupied by the concrete foundation, since the unit weight of concrete is more than that of the soil, there is a small increase in the stress level. Well, it is possible to take this into cognizance, but however, for illustration of the computation, I shall be ignoring the increase in stress that is arising due to concrete. I shall take the stress as purely that due to the soil, but however, the increase in stress due to concrete, replacement of soil by concrete, can be very easily taken into account in the same procedure. Okay. Now, what is the vertical stress at A due to the overburden? Remember that there is a dry soil layer and a saturated soil layer. Water table is somewhere in the middle, and wherever the soil is saturated and below the water table, you have to take the buoyant unit weight, and therefore the intensity of pressure at A due to the overburden will be gamma T into H1 for the dry part and gamma buoyant into H2 for the buoyant part, that is 102 kilonewtons per meter square. And similarly, at B you can calculate the intensity of stress due to overburden as 158 kilonewton per meter square. What is the settlement therefore? Settlement is summation of settlement at A and settlement at B. What is settlement at A? Cc upon 1 plus E0. E0 is given to be 0.4, so 0.54. So 1 plus E0 is 1.54 into the layer, let us say, is doubly draining. Then the drainage path length which comes here is only 7 meters. Log of P0 plus delta P upon 102 plus 7 into log 158 plus 0.16 into 22.5, where 0.7 into 22.5 is the influence coefficient into the intensity of pressure below the foundation. Similarly, at point B, 0.16 is the influence coefficient and 22.5 is the intensity of pressure. So, this gives you 44.9 millimeters. I must mention here that the settlement calculation involves the total thickness of the soil layer, whereas the rate of settlement includes the length of the drainage path. We are at the moment calculating the total settlement, and therefore, the value of 7 that has been used here and the value of 7 used here are both nothing but thicknesses of the upper layer and the lower layer respectively. To continue the solution, if you remember, there was one more aspect which was asked for, that is, what is the time rate of settlement if there is one-way drainage and if there is two-way drainage, or it is also called single drainage or double drainage. As you know, the difference only comes in the length of the drainage path. If it is single drainage, the length of the drainage path is the total length of the layer, or rather the total thickness of the layer, whereas if it is doubly draining, half the thickness of the layer is the length of the drainage path. Accordingly, we know there is a formula for T90 equal to Cv small t90 upon h square, and T90 from theoretical computations in one dimensional consolidation theory comes out to be 0.848, as we very well know. So, using that value, 0.848 into 14 into 14 T90 into h square, that is, divided by the given value of Cv 200 meter square per year, will give you 9.97 months as the time required for 90% consolidation in the worst case, that is single drainage case. In the better case of doubly draining one, it takes place much faster and it only takes 2.49 months. Let us take one more example on percent consolidation. I am still talking about primary consolidation. Here a building was built during a time period starting from March 1998 to March 1999. The settlement at the end of September 2000 was 3 centimeters. That is, after the construction was complete, the settlement was being monitored and it was found that at the end of September 2000 the settlement was 3 centimeters. Now, can we predict the settlement at the end of December 2013? Today we are in 2006. Can we predict the settlement at the end of December 2013 for this building? Certainly we can. Now, it is given that the total settlement is 15 centimeters. Theoretically it takes place in infinite time. So, given this total settlement 15 centimeters, how much of it will take place in 2013 can we estimate, and also that means compute the time required for 90% consolidation. So, how do we solve this? Now, you see here the load varies from 0 to its final value during construction, and therefore, what is the really load and what can be considered as the starting point for the application of the load. Since the load varies from 0 to its final value over a certain period time, say t, it will be reasonable, I am sure you will agree with me, to take t by 2 as the time at which we can take the total load to have become effective. That is, the average load is acting at t by 2, and so since the load is varying from 0 to its final value, we can take the load to be acting at t by 2, total load to be acting at 2 by 2. Now, what is t by 2? It turns out to be beginning of September 1998, okay, because the construction varies from March 98 to March 99. If beginning of September 98 is the point at which the load application takes place, then it is given that 3 centimeter settlement takes place at the end of September 2000. Okay. So, beginning of September 98 to end of September 2003, 3 centimeter settlement has taken place. What is the settlement that will take place in the year 2013 at the end of the month of December? We can follow a simple relationship which follows from one dimensional consolidation theory, that is settlement 1 divided by settlement 2, that is settlement at the end of September 2000 to settlement at the end of December 2013, which is required. Obviously, it is directly proportional to the degree of consolidation that takes place in the first instant to the degree of consolidation that takes place in the second instant, and we know that the degree of consolidation is proportional to root of time factor, and therefore you can say u1 is to u2 is as root of t1 is to root of t2, and capital T is directly related to small t, and therefore we can say S1 is to S2 is time taken for S1 under root to time taken for S2 under root, where 1 and 2 correspond to the years 2000 and 2013. Here T1 is 25 months, that is, if you start counting from the point of application of the load and count up to end of September 2000, you will get a total of 25 months. Then if you calculate now further up to December 2013, from the beginning of application of the load, you will find it involves 184 months. So, if at the end of 25 months 3 centimeters is the settlement, at the end of 184 months what is the settlement? Obviously, it will be 8.14 centimeters. Now, we still need to compute the time taken for 90% consolidation. We know the total consolidation 15 centimeters, we just need to calculate the consolidation that takes place at that is the time taken for a consolidation of 90%. We know that 8.14 is the settlement that takes place at the end of December 2013, and the final settlement is 15. Obviously, it must be in the same ratio as U1 is to U2, where U2 now is 100%, because 15 centimeter corresponds to 100% settlement. So, from this we find that the degree of consolidation at 8.14 centimeter settlement is 54.26%. If that is 54.26%, again using the same ratio, we can say that 90% of 15 centimeter settlement will correspond to a T90 of 42 years and 2.1 months. Now, this is a dramatic indicator of how slow a consolidation process can be. You just see here, since no sand drains are used, this building, which is constructed over a period of some 1 year or 13 months, settles continues to settle for a period of up to 42 to 45 years. 100% consolidation theoretically takes place in probably infinite time, but in practice it may be as high as 50 years. This could be very critical or dangerous for the structure, and a structure may not necessarily be able to withstand this. So, it is for such instances that we go for preloading and radial consolidation. Let us take a couple of examples on radial consolidation now. Examples 10 and 11 will be on radial consolidation. Let us read example 10. There is a 5 meter thick clay layer, and above that a sand bed, and below that an impervious rock. Immediately the indication is that it is a one-way drainage situation. It is preloaded with sand drains of 30 centimeter diameter at 2.7 meter spacing. Without sand drains, the degree of consolidation is 20% at any given time. What will be the increase in degree of consolidation if we install sand drains? For convenience, let us take CV for vertical direction as well as radial direction as equal, and as far as the sand drains are concerned, which are of 30 centimeters diameter and at a spacing of 2.7 meters, let us consider both possible arrangements, that is the square and the triangular arrangements, and then find out if U is 20%, what is the corresponding U with radial consolidation, and therefore how much improvement is taking place in U. For a square arrangement, we know that the parameter small l is 2.7 meters and capital R will be 0.564 L, that is 1.52 meters, and small rw, the radius of the well sand drain, is 0.15 meter. That means the parameter n, small n, which is the ratio of capital R to Rw, is approximately 10. We know that U is 20% without sand drains. That means it is nothing but vertical consolidation. That means U equal to 20% without sand drains is nothing but Uz with sand drains. So, with sand drains, if Uz is 20%, the corresponding T can be calculated as 0.031, and T20, small t20, that is the time taken for 20% consolidation, will be capital T20 into h square by CV z. That gives us capital the time taken for 20% consolidation as some value, and the corresponding time factor as 0.0838. Now, what am I trying to do? I know that the consolidation, vertical consolidation without sand drains is 20%. what I am trying to do is I am finding out for that vertical consolidation what is corresponding TV. For a UV of 20% or UZ of 20%, what is corresponding TV and what is corresponding small t 20. Now, at the same time, if sand rains are provided, what will be TR? At the same time, what will be TR, and therefore what will be UR, and therefore what will be U, and then we will compare this U and UZ and see how much this U is more than UZ, and that is what the intention of the calculation is. What is the additional gain that we get in view because of the consolidation arising out of radial drainage. So, for a square arrangement, a similar calculation will show that TR is 0.0838 and UR is 0.34, and this gives us 1 minus U equal to 1 minus UZ into 1 minus UR. As I mentioned just now, it gives capital U as 0.528, which means from 0.2 we have reached a value of 0.528 because of this radial consolidation arrangement, and that means there is an increase of 136% over the node sand rain case. Now, let us consider triangular arrangement in an identical manner corresponding to L and capital R and small n. We can find out UZ and TV and small t20 and T capital R, capital TR, that comes to be 0.096, and given this value of TR and corresponding UR, we get capital U is 50.4%. That means over a UZ of 20%, now we have got an increase of 152% in the degree of consolidation. Just take a look at the previous slide once again. With square arrangement we were getting 136% improvement, and with triangular arrangement we get 152% improvement. So, that is the advantage of the pattern of arrangement of the sand drains. Triangular arrangement makes the drains a little closer and the zone of influence covered is more per sand drain, and therefore we get a better improved consolidation performance with sand drains. We will take a look at example 11. Let us take a look at the next example, that is example 11. This is an interesting case study from one of my experiences. The example reads like this: the soil profile at a site near Calcutta is given in the next slide. Let us assume that the layer 5 in that profile is the only compressible layer. The settlement due to the load that is expected due to a structure there is 30 centimeters, but the permissible value is only 2 centimeters. The structure is so critical that its weight causes 30 centimeter settlement, but we can tolerate only 2 centimeter settlement. It is proposed to therefore preload this site by constructing an embankment which will impose an effective vertical stress of 100 kilonewton per meter square at the center of the compressible clay layer. Now, what this means is the size of the preload and the embankment is decided, the stress that it will induce is also decided, pre-decided. It is 100 kilonewton per meter square. Now, the question arises, how long this preload should be kept so that it will take care of all the settlement except that 2 centimeters which is permissible. The advantage is, if out of a total expected settlement of 30 centimeters, if 2 centimeters only can be permitted, the remaining 28 have to be nullified by this preload. Preload should be kept long enough to cause 28 centimeter settlement, and then once you remove the preload and replace it with the actual structure, there will only be a settlement of 2 centimeters, which is well within the permissible value and the capacity of the settlement, the capacity of the structure to adjust to. the settlement. Now, the question asked is estimate how long the preload should be applied, and the other conditions are sand drains are used, they are of 30 centimeters diameter and they are at 2 meters center to center, and the pattern of arrangement is given as square, although in the previous example we saw that triangular is a better option. Here in this case the square option has been utilized. Once again, for convenience, take CVR and CVZ as equal and of magnitude 8 into 10 raised to minus 4 centimeter square per second, and it is also given that the coefficient of compressibility MV varies with stress as shown in one of the figures that follows. So, this is the subsurface profile. There are 5 layers. First layer is a silty clay layer, second one is also a silty clay layer, the third one is a mixture of silty clay, then fourth is sand, fifth is silty clay, and once again the next layer below the silty clay layer is sand. That means it is a doubly draining layer. This given 20 meter thick silty clay layer is the compressible layer, layer number 5 is the compressible layer, and it is a doubly draining compressible layer. Then the value of MV in meter square per kilonewton is varying with pressure intensity as shown by this yellow line. So, now what this means is we have to find out what is the increment in pressure that arises due to the preload over and above the overburden pressure that is already existing at the center of the compressible layer, and then corresponding to that we should find out the value of MV from this relationship which has been arrived at from an odometer test. Once we know MV and once we know the increase in pressure that is coming due to the preload, and once we know the thickness of the clay layer H, we can compute the settlement as MV delta P H, because MV is nothing but a parameter which indicates the compressibility for a given intensity of pressure. So, the solution of this example is, take for convenience gamma to be same for all the layers, take H to be 10 meters, then at the center of the clay layer, silty clay layer in this case, then the initial pressure, overburden pressure is gamma H, which is 540 kilonewton per meter square. Then the increment in pressure is already given due to the preload, is 100 kilonewton per meter square at the center of the clay layer. Now, if this were not given, then either we can take the intensity of pressure at the center of the clay layer to be about the same as at the top surface, or that is valid provided the preload is of a very large size and it is usually of a very large aerial extent, or alternatively if it is of a very small aerial extent, we have to use Boussinesq's theory and compute the intensity of pressure at any given depth due to a given intensity of pressure at the surface. Now, MV for this increase in pressure, which is 640 kilonewton per meter square, that is overburden pressure is 540, additional pressure coming is 100, that means 540 plus 100 or 640 kilonewton per meter square is the net pressure. The load range is therefore 540 to 640, and the MV value corresponding to this from the graph shown in the previous slide is 0.0002 meter square per kilonewton, and corresponding settlement therefore is MV delta P H, and that is 40 centimeters. Now, this is the settlement that is arising due to application of a preload which produces an intensity of pressure of 100 kilonewton per meter square at the center of the compressible layer. Now, out of it is capable of producing 40 centimeters, but the original structure itself is producing only 30 centimeters. It is expected. Computation due to the structural load, similar computation shows that 30 centimeter is all that the total settlement is going to be. So, actually we do not need such a high preload which will produce a settlement of 40 centimeters. We could do with a slightly lower intensity of pressure and a smaller preload. However, let us say that for safety's sake, we will continue with this embankment which produces 40 centimeter settlement. Now, the settlement due to the structure which is expected is only 30 centimeters, but let us adopt 40 centimeters settlement and the corresponding preload. Now, out of this 30, 28 must be caused by the preload, 2 can take place during the lifetime of the structure itself. So, the degree of consolidation total that is required is 28 by 30, that is 93.93%. So, 93.3% of the settlement should take place with the help of the preload. We need to determine what is the duration that is required for this to achieve 93.3% consolidation. Now, it is known that when t equal to 1 year or 31.5 in 10 raised to 6 seconds, then for this given value of CVZ and t equal to 1 year, we find that capital TV is 0.0252 and UV is 0.18. That means, at the end of 1 year, the vertical consolidation that takes place is 0.18. Now, corresponding to this vertical consolidation UV, we will find out what is the corresponding TV and then TR, and then find out corresponding UR. Okay. The procedure is the same as we adopted for the previous example. So, given square pattern of consolidation layout of the sand drains, we can calculate for a given value of capital R by small r W, we can get TR equal to 0.495. If TR is 0.495 and N is 7.5, that gives us UR equal to 0.95 from Barron's chart. What it means is, when UV is 0.18, corresponding UR is 0.95. That means, the net U, total U is 1 minus this into 1 minus this minus 1, that is 0.964, whereas what we needed was only 93.3%. So, this shows that if the preload is kept just for 1 year duration, we get 96.4% degree of consolidation. That means, keeping the preload for 1 full year is sufficient to induce the 28 centimeters of settlement that we want. Now, this is certainly on the over safe side. First of all, the total settlement for the preload is 40 centimeters, whereas that due to the structure is only 30. We can therefore reduce the preload required. Similarly, the duration of 1 year produces 96.4% consolidation, whereas we want to achieve only 93.3. So, we can probably save in time. Instead of 1 year, we may keep the preload for a slightly shorter duration, which can be computed accurately. Now, what this means is, from a practical point of view, we have to exercise a judgment now as to really how much preload must be applied and for what duration. A more rigorous computation can be made rather than this approximate computation, and we can arrive at probably some savings in terms of preload and in terms of the duration of application of the preload. If required, it can be attempted, but very often in practice, if the difference is not very significant, we go with these over safe considerations. Now, with sand drains and without sand drains, if we want to compare, we have just now seen with sand drains we are getting 96.6%. Suppose sand drains were not there, then UV will be the only consolidation. We will not have any radial component added to it. So, taking only the time corresponding to that, that is 90% of that, we find 90% of the consolidation takes place in 33.8 years. That means 90% of the consolidation takes place in 33.8 years without sand drains, and 96.4% takes place in just 1 year with the help of sand drains, and that is the degree of improvement, that is the degree of advantage that we gain. Now, let us go back to one of the slides we saw in the very early stages. I had listed as usual a set of questions which I sought to answer. Now, what is consolidation and what is settlement we have answered in very great detail explicitly, but the remaining 3 questions, why is consolidation important, where is it important, and how do we compute, have also been now answered during the course of the last few lectures, and therefore, really there is nothing much to discuss. We know now the importance of the consolidation, we know where it is important. However, let us see some examples and some idea about the importance of this. The importance of this can be highlighted with the help of 2 dramatic special situations. Let us take the example of Leaning Tower of Pisa. Almost every one of us knows that this is a remarkable world tourist attraction. What is special about this is, one side of this Pisa tower has undergone settlement due to a compressible soil layer below it, and this has recently been rectified, and it has been ensured that it will remain tilted and stable at a particular degree of rotation. Now, why did it settle? Let us understand. In the first case, some details. The subsidence due to the clay layer below is 1.89 meters. That means one side of the tower tilted by 1.89 meters. This means that the north and the south sides had a differential settlement amounting to the difference between 1.86 meters and 3.75 meters respectively. The tilt that took place because of this is 5.5 degrees towards the north, because the north has subsided more. This means that the 7th cornice, you know there are several levels, 7th cornice protrudes about 4.5 meters over the first cornice. That is the amount of lateral movement that has arisen because of this settlement. Now, what is the reason for this settlement? You can see a lot of details about this, including the details of restoration of this, in the website which I have listed here. The prime reason is the under subsurface condition. There is a layer A which is 10 meters thick, which is basically consisting of deposits of sandy and clayey silts. Okay. Then below that there is a layer B, and below that a layer C. Layer B consists of sensitive, normally consolidated marine clay. So, this is the culprit. Below this, layer C is dense sand, and there is a water table in horizon A, that layer A. Now, these are the culprits, and you can see in this diagram that layer B has settled, and that is the reason why the tower has tilted. If the tower had undergone uniform settlement, perhaps it would not have been a serious concern, but this differential settlement leading to tilting had become a serious concern. Similar example one can see in Mexico. For example, this Palace of Fine Arts in Mexico City had a staircase leading to the entrance from the ground level. Now, today the staircase has gone below the ground level, and you can directly access the building at the ground at this level. What was the first floor level earlier has now become ground floor level, and there has been a total settlement of about 10 feet in this over a duration ranging from 1904 to 1972. The reason for this enormous settlement is the subsurface profile. The entire Mexico City is located in lacustrine deposits consisting of alternating layers of soft clay with igneous matter such as volcanic ash, some sand, some tuff, pumice, and some gravel. these alternating layers of soft clay with all interspersed with other igneous matter and all under a lake, formed under a lake, have given rise to the compressibility, owing to which buildings in the Mexico City area settled by as much as 10 feet, many buildings underwent a lot of settlement, and today of course, because we are very well aware of what is consolidation and how it takes place, and we also know how to take care of it, how to combat it, we are in a position to construct buildings which do not settle. However, in the past, Mexico City was very famous for such instances of buildings settling by a large amount. Now, there can be many number of cases like this. Wherever there are marine clays, there are structures, coastal structures such as refinery storage structures, container yards, and even other buildings and other structures. They are all highly compressible. London blue clay is a very well known example of a compressible clay. Bangkok clay is again another example of a famous compressible clay. Now, these are all very special instances about which there is a lot of literature available today, and I would very much advise you to go through that literature. Now, what are the different types of settlements? Immediate, construction, consolidation, and then total. We know what is total. We know what is differential, we have discussed. If you apply a load, some settlement takes place immediately, which is of an elastic nature and can be computed by elastic theory using this formula. And when you construct the building, as the load gets applied, also some settlement takes place, and that is known as the construction settlement, and all other terms are very well known to you. Now, there are a number of terminologies which I would advise you to go through. There is one list here: one dimensional consolidation, odometer, primary, secondary consolidations, lags, hydrodynamic and plastic, excess hydrostatic pressure, then all the coefficients of compressibility, then terminologies such as consolidation settlement and time factor, then special terminologies like normally consolidated, over consolidated, preloading, radial consolidation, and so on. And then with this background, you should be able to solve a few exercises on your own. There is one self-assessment exercise. I would advise you to read this carefully. You are required to calculate the total settlement of a footing. The answer is already given here, 32.7 millimeter. I would advise you to calculate this and confirm and satisfy yourself that you are aware of settlement computations. This is the illustration of the footing resting on a sand layer and a compressible clay layer, followed again by a sand layer. So, this is an instance of two-way drainage. Another exercise is there. Again, calculate the total settlement below a raft. Answer is 290 millimeters. This is the illustration. Again, there is a clay layer. Above that is sand, below that is impervious rock. So, this is an instance of single drainage. Then we have an assessment exercise 3, in which we have to obtain the settlement at the end of several time periods, 1, 5, 10 and 20 years. We can compute this as shown in the partial answers I have given here already. You can see that and convince yourself. So, in this lecture today, we have seen a number of additional examples. We have seen some general information of special interest, and I have summarized the entire phenomenon of consolidation and settlement. Thank you. There are a few references, you are advised to go through them.